next we're going to build toward a result called the extreme value theorem. But before we talk about the extreme value theorem, we need some language. And that language is contained in this definition. So here, consider this graph f on 0 to 6. Guarantee that 0 showed up as I said 0. This is a graph of f of x, and we're looking only at the piece of the graph between 0 and 6. So we're looking at that piece, starting at x equals 0, ending at x equals 6. We say f has an absolute maximum. These dotted lines mark off points on the graph. I'm marking off this point, that point, and 0, 0. We say f of x has absolute maximum. The absolute maximum is the highest the function gets, the largest y value. And we say it has absolute maximum, maybe I should say it like this. On 0 to 6, comma, we say f has absolute maximum of 7 at x equals 6, the highest point. We say on 0 to 6, f of x has absolute minimum, the lowest point, absolute minimum of 0, when x equals 0, at or when. When is probably a better word, but I don't want to erase at 4 times and write when 4 times. We say f has local maximum. Now what's a local maximum? Well, with this graph, we're going to interpret it as a local maximum as a top of a mound like that. That'll be what's known as a local maximum. And in this case, that occurs right here at 5 when x equals 2. And similarly, a local minimum is going to be the bottom of a mound. And these are actually going to drive a good deal of this week's work. I mean, I guess it didn't in the previous videos, but in this one and optimization and graphing, that diagram is going to show up a bunch of times. And we say, so the local minimum occurs at 4, and it's the local minimum of 3 at x equals 4. Now, for more language and interpretation of what this means, if we considered the entire interval 0 to infinity, so starting here and going off to that arrow, notice it goes to infinity by that arrow. So you might be tempted to say f has absolute maximum infinity, but in that case we will say f has no absolute maximum. And similarly, if it goes off to negative infinity, we'll say it has no absolute minimum. But what if we looked at 1 to 4? Well, I didn't mark off 1, but it actually doesn't matter. 1 to 4 would be the piece of the graph like this. Well, I will tell you, the extreme value theorem guarantees an absolute maximum and an absolute minimum on this closed and bounded interval 1 to 4. Which again, maybe I should put a line here, starts there and ends there. What is the absolute maximum on 1 to 4? Well, the absolute maximum, the highest this piece gets, is this. So in this example, on 1 to 4, the local maximum is also an absolute, say the absolute maximum. I botched up writing maximum there. So a local maximum could be an absolute maximum. And we'll see that. But let's describe local maximum and local minimum a little in a little more detail. The word local in math is an important word. And local means that it occurs in a small neighborhood around it. So on the previous board, when I drew this next to local maximum and this next to local minimum, I should have noted what I'm about to note. Local means it is the local maximum means it is the maximum of all points close to it. So while it's not the overall maximum in that curve, in the function from that previous example, close to that point, it is the largest value. And similarly for the local minimum, close to that point, it is the smallest value. Now there are a few different ways a local maximum and local minimum can look. Let's draw a couple. Right there. Local max. I'm going to call that F. I'll just call that F. So it could look like the top of a mound like that. Right here. Local minimum. Bottom of a mound like that. Well, what if we had a corner? Well, there you go. Local maximum. That still is the largest value of all points near it. And what about something like that? Well, down here we have a local minimum. Now, in all of these curves I drew, they happen to also be absolute maximum, absolute minimum. But what we want to observe is types of function behavior that could lead us to concluding that there's a local maximum or a local minimum. And you notice top of a mound, bottom of a mound, top of a point, bottom of a point. And we combine those using, well, we combine them into this observation because we can interpret all of these points using the derivative. Very important. What is the derivative evaluated at this x value? 0. What is the derivative evaluated at that x value? 0. What is the derivative evaluated at that x value? Undefined. What is, I don't need that. What is the derivative evaluated at this x value? Undefined. So we see that we can find where local maximum and local minimum values occur by finding where the derivative is 0 or where the derivative is undefined. Now, if you find a point at which the derivative is 0, you don't necessarily know until, we won't talk about it until, I guess you can conclude in the graphing section. We'll talk about it in more detail in optimization. But if you find where the derivative is 0, you don't immediately know if it's a maximum or a minimum, but you do know that it will be one of them. And that's one of the things we want to do in this extreme value theorem section. So this remark at the top is what I just said. We notice a local maximum or local minimum will occur at a point where the derivative is 0 or undefined. And those are important points. So we're going to call such an x value a critical point, an x value where the derivative is 0 or undefined, a critical point. And let's just look at this example. Find the critical points for this function. Well, we need where the derivative is 0 or undefined. So let's find the derivative, set it equal to 0. We find where it's undefined. Derivative, negative 2x plus 3 plus 0. We want to set this equal to 0. Add 2x, divide by 2, or subtract 3 divided by negative 2. You get x equals 3 halves. So that's where the derivative is 0. In this case, I mean, when it's undefined, I mean, if you have a fraction, it's going to be undefined somewhere. A fraction as your derivative. You know, like if you had a 1 over x, you'd have x equals 0. But in this case, it's never undefined. So I'll just say is the only critical point since f prime is never undefined. That says undefined. Let's make that look like a D there. So x equals 3 halves, the only critical point. We found where it's 0 and it's never undefined. Now, before stating and using the extreme value theorem, let's observe 2 more graphs. Let's make some observations about these graphs. Now, the goal of the extreme value theorem is going to be to find absolute maximum and absolute minimum. And we need the local maximum and local minimum in order to find them in most cases. So let's look at where on this graph and this graph the absolute maximum and absolute minimum occur on the intervals a to b. So we're only looking at the shaded portion of these graphs. Where do the absolute maximum and absolute minimum occur? Here, meaning in this first graph, the absolute maximum occurs where? Highest point is at B, at an endpoint. So we're looking at, maybe I should say, on A, B. We're looking on A to B. I could have said it occurs at B, but I'm just saying for now it occurs at an endpoint. The absolute maximum occurs at an endpoint, and the absolute minimum occurs at a point. Where is the minimum? On this interval, the lowest it gets is down here, where the derivative is 0. So the absolute minimum occurs at a point where f prime equals 0. Okay, that's one observation on one graph. What about the second graph? Where does the absolute maximum occur? This is supposed to come to a point. And with shading in, it might not look like a point, but that's a corner. Where does the absolute maximum occur on A to B? Well, the highest point is there. Here, the absolute maximum occurs at a point. I did the same thing when writing at A. I wrote A, and then had to squeeze in a T. I don't like that. I don't like that I had to do that. It looks okay, I think. Up close it looks okay. Where was I? Here, the absolute maximum occurs at a point where f prime is undefined. And the absolute minimum occurs at, where's the minimum on A to B? Well, the lowest it gets is over there at an endpoint. Those are important observations, and we're going to see why they're important when I fill in this fourth board. But before doing that, let's state the extreme value theorem. If f is continuous on the closed bounded interval, bounded meaning it doesn't go out to infinity, on the closed and bounded interval a to b, including the endpoints, then f attains an absolute maximum and an absolute minimum on a b. Maybe I should have said somewhere on a to b. That's okay. So all we need is a continuous function and a closed and bounded interval. Again, bounded meaning no infinities. Don't worry too much about that. If we have a continuous function on a to b, all we need is for it to be continuous, given that the function hits a highest point on that interval and a lowest point. And we'll notice here that the highest point could occur at an endpoint. The highest point could occur where the derivative is undefined. If this were rounded off up here, the highest point could occur where the derivative is 0. And also, the lowest point could occur at an endpoint. The lowest point could occur where the derivative is 0. If this is upside down, the lowest point could occur where the derivative is undefined. So all we need to do to find an absolute maximum and absolute minimum is follow what I just said. And I'm going to write that in a few steps, maybe 3 steps. Step 1, find critical points. And I usually don't like describing things with words because I think that just puts extra things in your mind. So I'll say where f prime equals 0 or undefined. Well, okay, it could occur at a critical point, but it could also occur at an endpoint. Find endpoints. How do you do that? Well, you look at your interval, and you take A and B. Step 3. Well, what's step 3? Our goal is to find absolute maximum, absolute minimum. Our goal is to find, the highest a function gets on a given interval and the lowest a function gets on a given interval. That's a terrible drawing. I'm going to erase it. Our goal is to find the highest and lowest it gets. We know from these that the highest and lowest points will have to occur at a point where the derivative is 0, a point that the derivative is undefined, or an endpoint. So all we have to do is compare the original function evaluated at all points found in 1 and 2. That's a lot of words. So I'll say at these points from 1 and 2. So let's do 3 examples. Example. Find the absolute maximum and absolute minimum of f of x on the given interval. First one we already saw, but let's complete it. Well, I'm going to go through all the details, but this is the one we found the critical points for earlier, 3s. So f of x is that function, f prime of x. I'm going to just write this work out again. Negative 2x plus 3, which equals 0 when x equals 3 halves. So now, step 1, find the critical points. It's never undefined. Step 2, find the endpoints, 0 and 2. Step 3, compare f evaluated at all of those points. And I like to list them like this in order. So we have the interval 0 to 2, so I like to do f of 0 equals, f of 3 halves equals, and f of 2 equals. What's f of 0? Negative 2. What's f of 3 halves? Well, we have negative 9 fourths, 3 halves squared is 9 fourths, plus 3 times 3 halves, 9 halves, minus 2. 9 halves minus 9 fourths is 9 fourths. Because 9 halves is twice 9 fourths. So it's the same as having half a pizza and taking half of it. You're left with a quarter. That was an only okay analogy. 9 halves minus 9 fourths is, what, 18 fourths minus 9 fourths. There's another way of explaining it. The negative 2 is still there. 9 fourths minus 2. You have 2.25. You get rid of 2. You have 25 cents. So that's 1 quarter. F of 2, negative 4 plus 6 minus 2, which equals 0. So we just found all of these points. Why are they useful? Let me just make sure these are right. I don't remember this actually being the right answer. Oh, yeah, it was. I didn't see that negative. When I just looked at that, I didn't see this negative. Yeah, okay. Where were we? We found the points. Now we just have to interpret them. So from this, we'll say, so f has absolute maximum. The largest, if you saw this as a positive 2 like I did, that would have been the largest. But it's a negative 2. Which is the largest y value? 1/4. Absolute max 1/4 when x equals 3 halves, and absolute minimum. The lowest, negative 2, 1/4 0. The smallest is negative 2, so absolute minimum negative 2 when x equals 0. So find the critical points, find the endpoints, and compare. Next, square root of 9 minus x on 1 to 9. B, let's write B, f prime of x. What's f prime of x? Well, we'd have a half 9 minus x to the negative half, but then you multiply by the derivative of the inside, which is negative 1. So f prime of x is negative 1 over 2 root 9 minus x. Another way of seeing that is by using the square root observation that the derivative of square root of x is 1 over 2 root x. But then you multiply by the derivative of the inside, and you put that negative 1 on top. I write this as one fraction here because I know we're going to have to do some algebra with it. We need where this is 0 and where it's undefined. Where is this 0? A fraction is 0 when the top is 0. So it's never 0. -1 is never 0. And is undefined when the bottom is 0. Undefined when the bottom is 0. Divide by 2, square, move the 9 over, you get x equals 9, because 9 minus 9 is 0. So we have no points where the derivative is 0, but it's 0 at x equals 9. Does it matter that the derivative is 0 at x equals 9? Well, we found our critical points, 9. Endpoints are 1 and 9. So all we have to do is find f at 1 and find f at 9. I just thought of a good final exam question. Let's find f at 1 and f at 9. I hope I remember that final exam question when I write it. F of 1, root 9 minus 1, root 8. F of 9, root 9 minus 9, equals 0. One of them is the max, one of them is the min. So f has absolute maximum, the larger number, root 8, when x equals 0, and f of x has absolute min. Absolute and maximum and minimum are all long words, so I abbreviate them: A, B, S, M, A, X, M, I, N. Sometimes absolute minimum of 0 when x equals 9. So with all of these, we're concluding information about the absolute maximum and the absolute minimum. Don't forget to conclude that information. Now let's do part C. Part C. Well, again, we need to find where the derivative is 0 and undefined. What's the derivative? 2/3 times 3x squared. 7 times 2 with a negative on it. 20. 0. We need to set this equal to 0. It's never undefined. It's a polynomial. But before setting equal to 0, I'm just going to take a 2 off of everything. Well, does that factor? 5 and 2 make 10, 5 and 2 make 7, and the signs work out. We want to set this equal to 0. When is this 0? Well, it's 0 when 2 equals 0. Never. When x minus 5 equals 0. When x minus 2 equals 0. Excuse me. When you talk for 4 or 5 straight hours, you inevitably get a sore throat. Well, I do at least. I mean, I get a sore throat when I do a 75-minute lecture. So we found where the derivative is 0. It's never undefined. I'm not even going to write that since it's a polynomial. So now we just need to compare the function evaluated at those and the endpoints. Uh, 0 to 3. F at 0, not f prime at 0, is -10. F at 2 is what? 16/3 minus 28 plus 40 minus 10. So what is that? 2 16/3 plus 2. 22/3. Sometimes I turn these into mixed numbers if we get a strange number here. F at 3, 2/3 of 27 is 18. 7 and 9 are 63. 20 and 3 is 60. Are 60. Well, make 60, I should say. And -10. And what do we get here? 18 minus 13. Is that right? 18? Yeah, 18 minus 13. So we have, what, -10, 7 1/3, and 5. And I'm going to make my conclusion over here because I don't have room over there. So I'll say that curly brace started out nice, but the bottom half isn't that nice. So f has absolute maximum largest value, 22/3, 7 1/3, when x equals 2, and absolute minimum, -10, when x equals 0. Now, with these, the process is the same. It's set up to be the same process. So practice the couple on the worksheets, and no, there is no mistake in this one. And this isn't this curve. You substitute 5, what do you get? I hope I set it up to be larger than 7 1/3. What happens if you get 5? F of 5 is 100, 250 thirds minus 7 and 25, 175, plus 100, minus 10. So what is, oh no, I set it up to give a minimum, well, whatever. What's 250 or whatever? Minus 85, is that right? 85 into that, get 5/3? Okay, I didn't set it up like that. Maybe it's on the worksheet, the one that, I don't know if that's right. But it doesn't matter if this is right. Why does that not matter? This question doesn't care what happens at 5. This question cares what happens at 0 to 3. So at 5, it could be way up here. But the absolute maximum and absolute minimum on the interval won't occur there because it's outside of the interval. So definitely be wary of that. I mean, there is one on the worksheet, and I have put ones on test where you find that point, and it gives you, like, f of 5 equals 6,000. And then you'd say the maximum is 6,000. But that's wrong because you have to look at the interval you're on. So try these examples on. I mean, it's the same process for all of the examples, but it's definitely one worth getting used to. And it's also good to have the visuals in mind with where the derivative is 0 and where it's undefined. I mean, I find that more important, especially as we go into optimization.